So I'll begin by briefly uh, reviewing what we did in first lecture, and then I'll continue with the second lecture. Okay, so in lecture 1, what we had seen, it was just a course on electrical machines, one of the most important courses in electrical engineering. And then, as you know, electrical machines is one of the foundations of the subject. So I have given the introduction and course outline, and of course you can refer to the syllabus for knowing what are the topics in it. Basically, I started by saying machines are two types: generators and motors. And then generator is nothing but one which converts mechanical energy to electrical energy, and then the motor is something which is one which converts electrical energy to mechanical energy. So in the energies thing, so there are three types of energies. One is the electrical energy. In between there is a field energy. This is the electric field, or it's a magnetic field. And typically in all our machines we deal with magnetic field. And then finally this ME is the mechanical energy. So what is happening is the electrical energy is converted into field energy, and field energy is in turn converted into mechanical energy. So this is a process that is left to right. Then that is a motor. And if mechanical energy is converted to field energy is converted to electrical energy. That process we are calling it as generator. So sometimes output is zero. That means if you consider motor as no load, then the mechanical energy may be zero. So entire electrical energy is converted into field energy. And similarly, sometimes generator is on no load. That means there is no electrical output. So the entire energy that is mechanical input is stored into the field. So these types of things are possible. Now considering losses. So what I have done, electrical energy is represented by WE, and field energy is represented by WF, and mechanical energy is represented by WM. So all these energies are measured in joules. So electrical energy is nothing but field energy plus mechanical energy. So this is in the case of a generator, and in the case of motor, this is WM is WF plus WE. This we have seen in the previous class. So now considering losses. So there are three types of losses. One is friction losses, windage losses. Other is copper losses, that is because of the I square R losses. And finally core losses. So all these losses are resulting in heating of the machine. So that is why all types of losses are heating. So now if you consider the losses, the diagram becomes something like this. So between electrical to field energy, copper losses exist. Inside the field energy, core losses exist. And finally, between the field energy to mechanical energy, friction losses and windage losses exist. So I hope this total is the losses in the energy. Now if I introduce the losses, then for the motor the equation becomes electrical input is equal to losses plus field energy plus mechanical energy. Or in the case of generator, mechanical input is equal to losses plus field energy plus electrical energy. So this is just a very brief overview of the energy conversion that is happening in the generator and motor. So apart from this, we have also looked at one more small example problem. So let me open that example problem. What we have done is started discussing what is a magnetic circuit, and inside magnetic circuit I said magnetomotive force is the source of the magnetic field, and MMF is measured in ampere turns, that is Ni. And then first example I had given, example 1, that is there are 8 turns. So you can count them. This is 1, 2, 3, 4, 5, 6, 7, 8 turns in this figure. And through a voltage source, I'm sending a 9 amperes of current in that. So total ampere turns in this is 8 into 9, 72 ampere turns. And then to determine the direction of the flux, we use the right hand thumb rule. So where you keep your hand such that the thumb is facing the direction of the current and the fingers will show the direction of the flux. So that is the thumb rule. Then in the example 2, we had one core with 3 coils. So A, B, C, 3 coils are given with number of turns 4, 6 and 5, and then different amounts of currents in different directions. So the question was to find the total MMF in the core. So that also we had solved. Then we looked at example 3, that is finding the reluctance. So reluctance symbol is S, and it is denoted by L by mu naught mu r into A. Anyway, I will review briefly once again all this, and then moving forward, we have flux in the core. Just a minute. Yeah. So we have flux, that is example 4. So we had calculated flux for both. So flux is in 6 microwebers. And then finally we calculated the energy stored. So today also we will be doing something similar. So finally, what you can see here is electrical input is 36 microjoules. Energy stored is 36 microjoules and output is 0. So this is briefly the review of the first lecture, what we had done in the first lecture. So I will stop here for 2 or 3 minutes. In first lecture, any doubts if you have, you are free to ask now. You can use. And today this lecture is about electromechanical energy conversion. So what I want to really talk about in this lecture is how exactly the electromechanical energy conversion is happening. And typically, this is like a kind of very fundamental thing. And if you open any textbook and then try to look at this topic, you will find sometimes it is a little bit too much into mathematics and it is a little bit confusing. So one of the conceptually confusing things I found. So in fact, when I myself were preparing for this, so I found that it was not very clearly explained. So in this lecture, I'll try to make an attempt to explain exactly with more clarity about what it is. So I hope this will be helpful for you and this will be useful for you. So let's begin, and you can always stop in between whenever you want to ask a doubt or you have any clarification. You can always stop me in between. So let's talk about this. So what I want to do is I'll give you some examples. So the examples of this kind of systems. So think of it a simple valve. So what is valve is, so let's say there is this there is a pipe here, and this pipe is having some kind of a valve, some kind of a gate kind of thing. So this thing can move up or down. So how this thing can move up or down is that, so there is some kind of it's connected to some kind of a core material. An electromagnet. Something like this. So here, so there is a winding. So, and then let's say there is a switch here. So now what happens whenever there is this, so is there's a water flow. So when I close this switch, when S is closed, so when S is closed, what happens? This switch closes and then current will flow in the winding, and this winding, this whole core will become magnetized, and let's say this become north pole and this becomes south pole, and in between there is another magnetic material, and it will get attracted and it moves upwards. So, and then it opens the valve, thereby water can flow from below. So this way, through the switch, I can control the water flowing in the wall. And if I open the switch, then again the magnetism is lost, and this thing will move down, and then finally it will close the switch, and then the more water will not flow. So this is one example where we are converting electrical energy into mechanical energy. So this is input is electrical, and here output is mechanical. So how the input electrical energy is converted to output mechanical energy. So this is one example. So another example is, let me give you another example. So this is something like you have an electromagnet like this, and then there is another thing like this, and then it is connected to a spring. So again, something very similar setup. I have a coil here, and then I have a voltage source. So the moment when I connect the coil, the voltage source, it will start conducting energy, and then it will attract this will become magnetized, and it will attract the particular piece here, and it goes this way. So this is again conversion of electrical energy into mechanical energy. So how we are converting electrical to mechanical. So you might have seen these kind of things. And then finally, of course, the obvious example, that is example 3, is just a motor. So you have a simple DC motor. So this is a DC motor. So I'll write M and draw a line. And then I connect a supply to this. Of course, there's a field winding also. The field winding also is supplied power. Then there is a mechanical output that is driving the mechanical load. So this is load. So this is again, input is electrical, output is mechanical. How this electrical to mechanical conversion is happening. So these are some basic 3 examples I had given. So there could be many more examples of this kind of thing. So far, any doubts about the mechanism I explained, how this is working? So I'll just wait for a minute. If you have any doubt, you can ask. So I got a message from AEC college that they are unable to see the drawings. So hopefully now you are able to see. I think this is just a specific problem to you. Are others able to see the board, the blackboard? Yeah. Okay. So let's continue now. So basically today my objective is to explain this. So the objective of today's next 1 hour, I want to explain how this particular example 1, how this particular system is working, where the energy is coming and where the energy is going, and so on. So in order to explain this, I would need to give you some basics of magnetic circuits. So let me begin by giving you that. So this is basically not the subject in this particular course, but it's just a brief review so that it will be convenient for you. So so if you want to understand magnetic circuits, you can just compare it with electric circuits. So where the EMF, electromotive force, is analogous to MMF, magnetomotive force, and it is nothing but N into I. This is in ampere turns. In fact, we had done this in the last class. So I'll not explain further in this, except that this ampere turns can be denoted by symbol F also. So this is about ampere turns. So the amount of current flowing in N. So N is number of turns in a coil, and I is current in the coil. What is, let's do some more quantities. So one is called mu naught. So this is nothing but absolute permeability. And the value of mu naught is, it's a constant, so it is 4 pi into 10 to the power of minus 7. So this is henries per meter. So this is a constant. This is related to the material that is being used in as a core for the coil. So if you have a coil, inside the coil you can have a core material. So this material. So for this material, there will be a relative permeability, and of course the absolute permeability is a constant. So there will be a relative permeability. So let me write that mu r. So this is relative permeability. So this is a constant for a particular material. Then there are two more things. So A is the area of cross section. So again, if you are using SI units, you should use meter square for this. And similarly, finally, L is the length of magnetic path. So given these values, now I can calculate something. What we can calculate is reluctance. So here I'm using symbol R for reluctance. Reluctance is directly proportional to the length of the magnetic path. So the more path the magnetic field has to be travel, the more reluctance it will be, because it's directly proportional, and inversely proportional to the area of cross section. So if the area of cross section is more, it is easier for the flow of magnetic flux. So therefore, this is similar to the resistance. If the area of, if a thicker wire is there, resistance is less. So something like that. And then the constant of proportionality is nothing but mu naught into mu r. And once you know reluctance, then I can find the flux. So flux is nothing but mmf divided by reluctance. So this is similar to, this unit is in Webers. This is similar to Ohm's law. So that is, current is nothing but V by R. So it is similar to that. This is like the similar to this. So now, once you know the flux, then you can also define what is known as the inductance. Okay. So I'll directly give you the formula. So inductance is nothing but this ampere turns divided by Just a minute. Let me just check my notes. Is a property, so that is defined as n square by r. So this also, now we know r value, so I can write n square into mu naught mu r a by l. So this is the inductance property of a particular coil. So if you know the number of turns, if you know the material, and if you know the area of cross section and the length, I can find the inductance. So what I'm doing is I'm just quickly giving you the formulas which we later use to find, to understand what is the process. Okay, so the another thing is energy stored. Energy stored in coil. So you might have seen this famous equation, half Li square. So this is the energy stored in the coil. This will be in joules. So if a coil of inductance L is carrying current of I, then half Li square is the energy stored in the magnetic field of the coil. So I can also change it slightly a little bit. So that is, so in the place of L, I can substitute this quantity n square by r. So then I'll get like this, and then here it is I square. So here this I can write half into n into ni by r. Sorry, ni square by r. Let me just something like this I can write. So here ni is n square I square, I have written ni into ni and then by r. So this ni by r is nothing but the flux, and this is flux. So this is another symbol we can use in the this. So where this is the energy stored in the coil. I'm writing E coil. Energy stored in the coil is this. So what happens is, now I think now we have all the basics available for us to study this. So what you can do is, how a coil works, or let me call it electromagnet. So how an electromagnet works is, so let's say this is a bar and then I have the winding on it. Now, so what I'm trying to show here is that this particular switch, which I close, so there will be some electrical resistance for this coil. So that electrical resistance equivalently I am writing here. So this is Req. So equivalent resistance of this particular coil I am writing like this, and some voltage I'll apply. So under DC conditions, like under say DC voltage, when I close the switch, so let's say this is 10 volts and let's say this is 1 ohm. So initially when I close the switch, there will be some inductance effect. The current will gradually rise, but then under steady state conditions, the resistance of this, anyway, I've shown this equivalent. Nothing but, so I will nothing but V by R. So this 10 amperes current is flowing in the turns. Let's say the number of turns is 20. So 10 into 20, 100 ampere turns are there. So that 100 ampere turns will result in some flux here. So that flux will be generated like this, and this whole core will become magnetized. So this is basically this. So to gain further understanding, let's begin by just we'll make a small plot, something like this. So on x-axis, I will keep Ni, and on y-axis I'll keep the flux. So when the N anyway is constant, so therefore when the current is zero, so the flux is zero. But so I can also introduce a variable resistance here. This variable resistance, I can control the current. So if I give 1 ampere, 2 amperes, 3 amperes like that, gradually if I increase the current, then the flux also will increase. So the relationship is like a straight line like this. So this is the relation between Ni and flux. Now this is a linear part. Actually after some time it becomes like this, because even though more ampere turns I am creating, that will not result in higher flux, because the core is already saturated. So this is saturation effect. But we are only discussing this part. This is the linear part of the curve. So again, if you see, so this is F. Actually, F is nothing but Ni, and this is flux. So then you look at this energy. Energy is nothing but, so at a particular point I have some F, at that point I have some flux. So energy is nothing but half into F into flux. So we had seen this. If I go up here, you can see that formula we just derived from this formula, that is half Li square. So this is the electrical formula for the energy stored, whereas this is the mechanical formula, half into F into flux. So therefore, now you see this is nothing but, what is the area of a triangle? Half into base into height. So now if I look at this triangle, so the base is F and the height is flux, and therefore this area is nothing but the area of energy stored. This area represents the energy stored. Similarly, you can look at this area also. So this is nothing but half into, so this is nothing but half into F into phi. So this is energy stored. And because there are two quantities, just to avoid confusion, this one is called co-energy. So if you draw this plot, relation between F and flux, then you can find energy and co-energy. Both are equal in a particular thing. So now if I increase the field strength, so the flux will also increase and more energy will be stored like this. So that is about energy and co-energy of a magnetic circuit. So far, if you have any doubts, you're free to ask now. So any doubts you have on this? So briefly, I had given review of magnetic circuits. I have written down some of the main points here, main formulas that are used in magnetic. So let's call this example 6, because in the previous classes we solved about 5 examples. So let's call this example problem 6. So the question is something like this. So So a coil has following parameters. So it is something like this. So this distance is 30 centimeters and this distance is 20 centimeters. But there is a small problem. There is a 5 mm air gap here. So let me write that here. Then the cross section area, this cross section area is like a square. So area is 10 centimeters cross 10 centimeters. So this is the distance calculated midpoint to midpoint. And then this particular material has a mu r of, let me write it in some other place, 1000. So this parameter. So the question is find the reluctance. So this is the question. So I had given all the required parameters to you. So based on this, can you find the reluctance of this particular pore? So you take 5 minutes, you can calculate it and then you let me know. So I'll also give you the formula for reluctance. This is nothing but L by mu naught mu r into A. So please take 5 minutes to calculate the reluctance. So this is like kind of a quick classroom work for all of you. Sharing my. So first, what are the parameters given? So look at the length. If you see, the total length is 30 below, 30 above, 20 on either side. So total length is 1 meter. So I'll say L equal to 1. So the units are in meters. So this is length in meters. Then mu naught. So I'll just write u0. So 4 pi into 1 e minus 7. So this is a constant I have defined. Then mu r, relative permeability 1000 given to you. So given these values, next what I can define is number of turns. I'm sorry, the area. So area is 10 centimeters by 10 centimeters. That means 100 centimeters square or 100 to the power of minus 4 meters square. So you convert everything into meter square. Then finally R equal to L divided by mu naught into mu r into A. So this is our simple program. So now if I just run this program, so on the right I can see the solution. So this is 79577 e to the power of 4. So let me shift that answer to my blackboard. Area is 100 into 10 power minus 4 meter square. So therefore R is nothing but L by mu naught mu r A. By the way, so I am forgetting the air gap here. So there is a small air gap also. So the calculation, this one is without air gap. So let me add that here. Find the reluctance of the coil A with air gap and B without air gap. So if there is no air gap, that means this completely is continuous. So then I'll have this formula correct. So here, how much I was getting? The answer that I was getting was 79577. So the unit for this is 1 by Henry. Or H inverse. So this is 79,577 is the reluctance of the uh, particular material. So now this is without air gap. Now if I consider air gap, then what happens is I'll get total reluctance will be reluctance of the core plus reluctance of the air gap. So what is the reluctance of the core? So reluctance of the core will be L. So the total length minus length of the air gap, Lg, divided by mu naught mu r into A. So instead of the total 1 meter length, I'll reduce the 5 mm in that. So what is the total length? 1 meter minus 0.005. So this is 5 mm is equal to 0.005 meters. So what I'm doing is I'm just reducing the length and then divide by this same thing, denominator, mu naught mu r into A. So how much I get it? So I'll just use my calculator. Length of air gap 0.005. So the reluctance now will become, so I'll just write one more, RC, reluctance of the core, that is nothing but L minus Lg. Then similarly RA, reluctance of the air gap. So the air gap mu r will be 1. So I have to simply remove the mu r constant here. I'll get this. And then the numerator only Lg will be there. And then finally total RT is nothing but RC plus RA. So I have all the code ready. So if I just execute this, so I got the results. So let me write this in the solution. So this is 79180 inverse H, and then R of air gap is much higher actually, 3,97,089, 890. So therefore, R total is nothing but addition of these two. So that I am getting 4,77,070 Henry. So this is the calculation of reluctance. So now, any doubts up to here? So what I have done is simply I have considered one is without the air gap, then the length is 1 meter, I can calculate that. And in the second example, I have considered the air gap. So with air gap, I got different value of reluctance. So let's continue. I'll continue this example and then we'll say example 7. If the above core is provided with coil of n equal to 100 and I equal to 10 amperes. Find flux. So now that is with and without air gap. So now what we have is, so one example is without air gap. So another example is with air gap. So in both cases, so the current is 10 amperes and number of turns is 100. Same way here also. N is 100, current is 10 amperes. So find the flux. So what is the formula of flux? Can you try? The flux is nothing but simple Ohm's law, ampere turns divided by reluctance. So can you find the flux in both cases? So I'll wait for your answer. So could you calculate the flux? So what is the reluctance for the case where there is no core? So the reluctance is 79,577. This was the reluctance we calculated. So here, so this is the case, the flux here. So what about the flux here? The same ampere turns, 100 multiplied by 10 amperes, but this time the reluctance is more. So the reluctance is much higher. That is 4,77,070. So this is 4 lakh 77,070. So how much is the flux in the first case? I'm getting 0.0125. So let me write these answers. 0.0125 Webers. And whereas here the answer is 0.00. Let me check my answer. 21 Webers. Or in other words, here I can write it 12.5 milliwebers, and here it is 2.1 milliwebers. So finally, one calculation let's do, that is let's call it example 7 or 8. Which one? Yeah, this is example 8. Find energy stored in both cases. With and without air gap. So can you find the energy stored in both cases? So what is the formula for energy? So energy is nothing but half Li square. You might have studied this, which is also nothing but half into F into flux, which is also nothing but half into Ni phi. So can you calculate energy stored in both cases? So what is the energy stored in both cases? With air gap. Okay, so let's summarize the solutions. Summary. So this is core with air gap, core without air gap. So what do you find? Magnetomotive force. So this is denoted by F. So here it is 1000, and here also it is 1000 ampere turns. So the magnetomotive force is exactly same. But what about reluctance? The reluctance here, it is 79,577. What is the reluctance in the other case? It is 4,77,070. And therefore, what is the flux here? I'm sorry, I think I just reverse the solution. So let me just delete this. I'm just, yeah. So this is 4,77,070, and this is 79,577. So what about the flux? So with air gap, the flux is less. That is, how much was the flux? 2.1 milliwebers. Whereas here the flux was 12.5 milliwebers. So therefore, here, what is the energy stored? WF. So energy stored in the magnetic field. How much is the energy stored in the magnetic field? Here with air gap, I was only storing 1.05 joules. And here I am storing 6.28 joules. So what is the final conclusion? So what is the final conclusion? For the same MMF, more energy is stored without air gap. So are you clear with this? So you have any doubts so far? If you have any doubts so far, please feel free to ask the doubts. I think on your screen you're able to see the next question. So what I'm showing in this question is that there is a small piece of iron that is denoted by letter A, and the dimensions of that is 5 mm by 10 centimeters by 10 centimeters. So what you notice, if I move the A upwards, it will exactly fill the air gap. So the dimension of the air gap is exactly same as the dimension of this A. So I want to move this A upwards. to fill the air gap. So the question is how much energy is required to lift block A up by 10 centimeters. So can you calculate that? How much energy is required to move this A upwards? How much energy is required? So to move any item upwards, you have to give potential energy to that item. So how much height I want to lift this item? So first thing is you have to find the weight of the item. So what is the weight? So, so what is the volume? It's nothing but 5 mm. So I'll convert into centimeters. So 0.5 centimeters multiplied by 10 centimeters multiplied by 10 centimeters. So I'm getting 10 into 10 is 100, 100 into 0.5 is 50. 50 centimeter cube I am getting. Now what is the mass? Nothing but density into volume. So what I'll get? So density is 10 grams per centimeter cube multiplied by 50 centimeters cube. So I'm getting 500 grams, which is nothing but 0.5 kilograms. And to lift this by 10 centimeters up, potential energy required is how much? Potential energy is mgh. So the mass is 0.5 kgs and the gravitational is 9.8 and the height is 10 centimeters or 0.1 meters. So how much is this? So this I calculated, it is 0.49 joules. So now you connect back all these things. Required to lift block A. So now if I combine everything, so now this is like the conclusion. So I have a core like this. And then I have N equal to 100 and the current of 10 amperes is flowing in this. So this is block A. So if block A moves up, air gap is closed. Okay. So energy in the field. So field energy with air gap is only 1.05 joules. Without air gap is 6.28 joules. And energy required to fill the air gap is only 0.49 joules. So if I just give 0.49 joules, so to fill the air gap, is only 0.49 joules. So the question is, do we have enough energy to fill the air gap? And the answer is yes, because this difference is 5. Almost 5.2 joules of energy is available. Out of that energy, some energy is used to pull the mass upwards. So this will move upwards. So this is how electrical energy is converted to field energy, which is in turn converted to mechanical energy. So did you understand the logic why it is? So if you have any doubts, please ask. So finally the conclusion is, because sufficient energy can be gained with the same ampere turns, so I'm having sufficient energy to lift the object up. So this is the final conclusion. So any doubts about this? So conversion. So this is how the electrical energy is converted to mechanical energy. So any doubts you have on what we have discussed today? So this electromagnet is still there with a coil. I have block A plus I have some mass. So the total mass here, let's say, is 2 kgs. So again the question is it possible to lift 2 kg mass? So again you find out the mgh. So the mass of this is 0.49 or 0.5 kgs. So total mass is 2.5 kgs. Total mass is 2.5 kgs. Then you see mgh. So mass is 2.5 and gravitation is 10. So 9.8 I am approximating to 10, and then height is 0.1 meter. So these two will cancel out each other. So 2.5 joules is required. Is required. Now the question is, do we have 2.5 joules available? Yes, the answer is you have 2.5 joules available, because the gap here 1.5 joules and 6.28 joules. So that much energy is available in the air gap. So therefore I am able to lift the object even if 2 kgs weight is attached to this. So if I want to make it continuous, so here this is linear, only one direction. So if I want to make it continuous, what I can do is, I have the core like this. I'll fix I'll fix a shaft, and around this I'll fix a magnet, something like this. So this is a shaft. To this shaft, I will attach a mechanical load. Now the same logic applies. In order to reduce the air gap, this will rotate like this and this will rotate like this, and the air gap will be reduced. And whenever you reduce the air gap in a machine, more energy it is stored in the magnetic field and more mechanical output you can get it. So the whole idea is to reduce the air gap between the magnetic field so that the reluctance is reduced. So earlier example is a linear motion, whereas this example is a circular motion, you are able to get it. So this is like the field and this is the armature, and in the armature you can rotate it. So we'll see more details about the machines in future. So any doubts so far in this lecture? uh, Electromechanical conversion. So through these examples, I try to explain. I'll try to share the notes of this lecture. So before attending the lecture 3, which is going to be on Thursday, so kindly review this. Thank you.